result
Oh,
was.
no. We did not finish it, I don't think. I think we got like halfway through the result.
Oh,
Yeah,
God.
that's it, yeah.
I'm
This
gonna
was the
check.
question.
I think at the end I got to understand, kind of.
Like what the process was gonna be, not necessarily even the
Yeah.
result, but the process. Right.
No,
Good.
not the result, but like understand what you were doing.
Good. That's all I really wanted, right? So, I mean, I thought we were going to get through the proof, and we didn't, just because we ran out of time. But what I'm mostly concerned with is that you guys follow me. You don't. What we're going to do today is going to lead us to, like I said yesterday, it's going to lead us to a result that you won't have to reproduce. You'll just have to use the result, right? And that's really nice. I'll show you. It's actually really crazy how much this simplifies. Which is really awesome because we have to get through kind of a tedious proof, but there's a means to there's an actual reason why we're doing this. All right, so let's see. I've got 6 slides here. I'm going to go ahead and just make a new one because it tends to lag if I have too many slides. So I'll make a new one. I'm going to see how charged my Apple Pencil is. 27. That's good enough. All right, and I will share my screen. I have not done that yet. And I just want to remind you guys what we were doing yesterday. When we left off, we were attempting to solve the second order linear homogeneous differential equation, right? So let me just remind you what that means. Just adjust my chair real quick. All right, so we were saying we're trying to solve the second order linear homogeneous ordinary differential equation, and that was just this following thing, right? So we're trying to solve the differential equation a d squared y dx squared plus b dy dx plus cy equals 0, right? This is the thing that makes it homogeneous. Or homogeneous, however you want to pronounce it. Okay, so we were trying to solve this equation. Of course, a, b, and c here, a, b, and c are constants. But let's make one constraint. The one constraint is that a is not going to be 0. Okay, because if a is not equal to 0, then this isn't a differential equation of second order anymore. It becomes a first order differential equation. Actually, it becomes a separable first order differential equation. So we're not going to care about the case where a is equal to 0. We're going to care about all other cases, right? It doesn't really change anything in our proof, but it's an important distinction to make. Okay, and so what we had said was we can think of this differential equation in sort of a different way, right? We can think of this differential equation. And in fact, all linear differential equations, you could do this. We can think of this as being an operator, right? The operator would be this thing. Operating on just y, right? So this is only possible because this is linear, right? Because this is a linear differential equation, because we don't have like a y squared in there or anything like that, we're always going to be able to factor out. It's not exactly factoring out a y, but you can think of it as factoring out a y. What we're really saying is here that because the derivative is linear, then we could operate on y each term by term, right? So we can think of this as being one big operator that's operating on y, because we can do it term by term. Okay. That again, this is like the crucial step. You're not going to need to reproduce this proof on an exam, but it's crucial in understanding what we're going to do, right? And then we said, well, assume that we're going to make a simplification, which is dividing through by a, right? I think we did that before last time. So we're going to divide through by a, and we'll end up with a slightly different operator. Yeah, I think we divided through by a before we did the like factoring out thing last time. Right? And then we could say, this is the kind of the weird part. This is the part we had left off on yesterday. We can say that this thing here, you can make some like a notational change. You can say let d equal d by dx. And then you can see this is just like d squared, right? That first term is d squared, because if you have d times d, right, or d of d, it's not really times, that would be the derivative of the derivative, which is the second derivative, right? And so writing it with this d notation makes it look just like a quadratic, right? We have this thing right here. That's what we can write our operator as. Right?
Sir, isn't it
Yes.
d without the square?
Yes, yeah, the second term. Yes,
Okay.
Thank you. I think what's going to happen here is it's probably going to not let me write. I'm going to have to close down again. Oh, no, it worked. Look at that. All right, so we have this quadratic now in d, this operator d, and we could write this quadratic because it's monic, right? Monic means that there's the coefficient of the squared term is 1. We can write this as d minus m1 times d minus m2 of y equals 0, right? Where, of course, m1, we could think of m1 as being like negative b plus the square root of b squared minus 4ac over 2a, and m2 would be the other one, right? But you could actually reverse the order. It doesn't matter which order you do it in. The solution is going to be the same. All right. Notice that we're not making any reference to whether or not the m's are real, imaginary, the same, so on and so forth, right? So we're just saying they're the roots to the quadratic. If you have to brute force it with the quadratic formula because it doesn't factorize or because it's imaginary, so be it, right? All right. So once we have that, what we did, and it seems kind of silly to even have introduced this d because we're going to undo the d basically. But the reason we use the d is just so that we could see that it's a quadratic, right? So you don't.
Sir,
Yeah.
it doesn't matter if we write d plus m1, d plus m2, or d minus and minus, right?
Right. So no, it doesn't matter at all. What you'll get is a different sign in your answer. But I'm doing minus because the standard notation is like when you factorize, it's like x minus a root times x minus a root. Right?
Sure. Okay.
Let's see what Javier just asked. A, B, and C, the quadratic formula don't equal the A, B, and C, the initial differential equation. Yeah, they do. They do. Yeah, they do. Because the roots, Javier, the roots, if you divide an equation like this, like if you divide a squared b plus bx plus c, ax squared plus bx plus c by a, you'll get the exact same roots. Yeah, b doesn't equal ba, but when you plug in b over a and c over a into the quadratic formula, you end up with the exact same formula.
Because you're just dividing the whole equation by a constant, so that doesn't change the
exactly.
roots.
That's exactly right.
What I want to say, yesterday I have the same question, but I don't understand. So actually, what does it mean? It doesn't matter where a is situated; it's in the equation, so nothing changes actually.
Yeah, exactly. I mean, you're dividing 0 by a, so you're not changing the equation at all. What will happen is that if you use b over a and c over a in your quadratic formula, it looks messier, but you'll still get the exact same roots. Right? So think about it. Like you'll have it would become minus b over a. I don't want to do the whole thing. Plus square root of b over a squared minus 4 times c over a divided by 2a. Right? What you're going to end up with is if you redo the algebra here, you'll end up with the exact same formula. Right? Or not 2a would just be 2, right? Right. And so what you're going to get is that you're going to get a factor of 1 over a on the numerator. This is going to be equal to like 1 over a times minus b plus the square root of b squared minus 4 times a times c over 2, right? So it's the exact same formula. Make sense, Javier? Javier? Okay.
But you were lagging.
All right. So I'm going to erase that because I don't want it to take up too much space, make it look chaotic. All right, so now we've got it in this factorized form. What I'm going to do is I'm going to do some renaming. Again, I'm going to say, let this, write it back the way that it was before, d by dx minus m1 times, it's actually of d by dx minus m2 y equals 0. And we're going to say, let this whole thing here, let that whole right set of brackets and y together be some new function omega, right? And if you want, you can call this omega of x to remind you that it's a function of x. I'm not going to write the x down each time because it's too much of a pain. But just we're going to call the entire equation, this is going to be, you can even think of it as expanded, right? But it's d by dx minus m1 of y, which if you want to think of it this way, you can write it as dy dx minus m1y, right? It's a naming convention. This is totally allowed. All right, and so what we then get is that we have our differential equation, our original equation. So the original equation becomes now simply by dividing through by a and doing this renaming, we end up with the same differential equation becomes d by dx minus m1 of omega equals 0, which we can expand this now. This is d omega dx minus m1 omega equals 0. And what type of equation is this?
Linear, separable.
Linear first order separable, right? This is a separable differential equation. We can solve this super easily by integrating. So let's do this on the next page. So we just have the equation go away PDF element, d omega dx minus m1 omega equals 0, where we have that omega is d by dx minus m2 y, right? So we'll keep that in mind. So what I've basically shown you, by the way, is that a second order differential equation, a homogeneous linear second order differential equation, can be turned into a system of two first order ordinary differential equations, right? And they're linear in this case as well, right? So that's really nice. That's kind of a fundamental thing. It turns out that any nth degree linear ordinary differential equation that's homogeneous can be turned into n first order linear differential equations, which is super nice because guess what? We solved all linear first order differential equations, right?
Sir, could you go
Yes.
back a slide, please?
Yes, of course.
Sir, does this work until like fifth order differential equations, like kind of like polynomials, or no?
As long as they are linear and homogeneous, then yes, absolutely. That absolutely will work. Well, with constant coefficients, right? Because they could have non-constant coefficients and still be linear. Constant coefficients are pretty important here for this general technique that we're going to be using. But in general, you can make pretty small modifications if they don't have non-constant, or if they have non-constant coefficients. But this theory will work, this exact theory will work without any modification as long as there are constant coefficients, right? You won't ever do a third order differential equation in FP2, but you could do it. You could do a third order linear homogeneous differential equation with constant coefficients using the exact same method.
Why
Yes.
why did you write a W instead of a Y in your final result?
Well, because I've renamed that whole thing in brackets, right?
Yeah, me.
I
Yeah.
renamed it. Ugh, I don't know why it's zooming in like that. It's never done that to me before. Whatever. So the whole point is that we're doing a change of variables to make it so it's a first order differential equation, right?
Yep.
Okay, so what we have now is a differential equation in omega and x, and then we have a differential equation that's in x and y, which we'll get to, right? Well, the other one's actually kind of in omega x and y, but we'll get to that one in a second. All right, so we can solve this omega x1 really easily. The omega x1 is just separable, so we can rewrite this as, hopefully this isn't skipping too many steps, as 1 over omega d omega dx equals minus m1. Everybody see how I got that? Just added m1 omega to both sides and divided through by omega. And then, of course, integrating here, we end up with an omega integral on the left-hand side and an x integral on the right-hand side. Okay? Which this is easily solved to be natural log of omega equals minus mx m1x plus c. And then, of course, we see that omega is just going to be e to the minus m1x plus c, which we're going to do our typical thing where we say this is the same thing as like a e to the minus m1x, just like that, right? But here what I'm actually going to do instead of writing a big capital A is I'm going to write a lowercase a. Just because
I'm confused. D omega by dx minus, that's a minus, right, at the very beginning?
Yep, it should be plus. You're right. Thank you.
So if you're moving it, it should be positive.
Yep. Let's remove a minus sign from all these. You're right. They're all gone now. That never happened. All right, so here I'm going to use a lowercase a just because I'm going to end up modifying this constant later on. And I know that I typically say like c times 3 is c when I'm just talking about constants, but here I'm actually going to make a change just because I don't want it to be confusing, right? All right, so we have...
So that small a gonna get confused with the other a?
We're going to end up... The small a is not going to matter in the long run.
Okay.
right? Okay, so now what we have is a solution to what omega is, right? We know what omega is, but we have another way of representing omega. So we have two different representations of omega that they have to be the same thing, so we set them equal to each other, right? There's supposed to be an underline under AE. There we go. So
Wait,
let's set.
I'm confused. Why are we using A?
It's a constant. It's e to the c, right?
Oh, okay. Sure.
Right? Just as we've done before, I'm just using a lowercase a instead of a capital A.
Okay.
Right? Yeah, I mean, I'll use a capital A if you want to see it more like the other ones. It's just that if I do a capital A, I'll have to do A times some constants later on, and I'll have to stay the same. But that's fine. I'll just use capital A. There's no problem. All right? Just as before then. Okay, so now we have to set these two things equal to each other because they're both omega. So we now have, I'll try and, no, I won't section off. We now have A e to the m1x equals, and now I am going to expand it out, dy by dx minus m2y. Okay, so that's nice because this is a first order differential equation. It's not separable, right? But it is linear, right? It's linear. We know how to solve all the linear separable differential equations, or not inseparable differential equations of first order. We use an integrating factor here, right? So I'll write this in a way that's more familiar to us. We usually see the d stuff on the left-hand side. So we're trying to solve the differential equation dy by dx minus m2y equals a e to the m1x. And of course, when we're using integrating factors, we have to multiply by mu. So we want to times by mu. But mu is just going to be e to the power of the integral of p of x, which p of x in this case is just minus m2. Okay, everybody follow that?
No, just seconds.
Can you repeat again?
Me?
So remember that when we so remember that when we're trying to solve a
not
different
me.
hold on. Alex, hold on. Let me finish a sentence. When we're trying to find the solution to a first order caveat, no, we will not have to recreate this. I've said this a million times. I'll show you. I'm going to show you how to actually use this result afterwards, right? I'm showing you where the result comes from so that you don't just think it comes from thin air. All right. So when we're trying to solve a first order linear differential equation that's not necessarily homogeneous, our method, the only method that we can use all the time, is to multiply by some integrating factor and force the left-hand side to be product rule, right? This is what we've been doing for the past like 3 days, 3 lessons. So when we're trying to find that mu, we can always use that mu is going to be e to the power of the integral of whatever comes in front of y, okay? In this case, the thing that comes in front of y is minus m2. All right. So once we multiply by whatever that mu is, which we'll simplify in a second, you'll see that the left-hand side automatically becomes product rule, and the right-hand side is going to become something that we can actually take the integral of. All right. Everybody clear with what we're doing?
Yep.
Okay. So this is going to give us just e to the minus m2x. Okay. It's a relatively simple mu. Not too complicated. So if we multiply the entire equation by this mu, we end up with e to the minus m2x dy dx minus m2 e to the minus m2x y equals a times e to the m1 minus m2, minus m2x, like that.
Sir, where does the plus C go?
We don't need a plus c when we're finding mu because we can use any plus c, so let's use 0 as our plus c. Right? Okay, so we have this differential equation now, and we can simplify the left-hand side to be product rule, right? The left-hand side, this is just the derivative of e to the minus m2x y, right? You can do product rule to see that this is actually going to give you the left-hand side of your differential equation, okay? And the right-hand side, well, it doesn't change yet, right? It's just e to the m1 minus m2x. Okay, and so now we're prepared to take the integral, right? Taking the integral of both sides. On the left-hand side is trivial. The left-hand side just gives us minus m2x y, right? And the right-hand side gives us, well, I'll write the integral out, a e to the minus, or to the m1 minus m2 x dx. So what is the integral of ae to the minus or to the m1 minus m2x?
A divided by m1 minus m2 e times e to the power of m1 minus m2x.
Good. Anytime we have, I'll put this in a little box up here. Anytime we have the integral of e to the power of ax, where a is any constant, this is always going to be 1 over a e to the ax plus c. That's exactly right. And so in this case, our a, that little like constant thing in front of x, is m1 minus m2. So this is going to be e to the minus m2xy equals a divided by m1 minus m2 e to the m1 minus m2x, right, plus c. Okay. All right. So then all we have to do to find y is just divide both sides by e to the minus m2x, or multiply both sides by e to the positive m2x, right? And so we end up with y equals, this is the part that I was saying I wanted to use little a before, but I'm going to say that this whole constant, rename this whole constant a again, right? Just because I'm going to use a and b, that's typically what we use. Just rename the whole constant a. Hopefully that's not too confusing. And what we're going to get is, our solution is y e to the m1 minus m2x times e to the m2x is just e to the m1x, right? So that the m2's basically cancel each other off. So we just get a e to the m1x. And then we're going to get for our next term, actually, you know what? Instead of using a c here, I'm just going to use a b. Just a different letter name, right? And for our second term, it's just a constant times e to the m2x. So our next term.
Or why is a divided by m1 minus m2 equal to a?
This is why precisely in the beginning I said I wanted to use the lowercase a. It's just renaming it again, right? It's an arbitrary constant, so we're going to name it something else.
Sure.
So we end up with this really simple solution to all second order linear differential equations that are homogeneous with integer coefficients, or with constant coefficients. This will always be the solution, although we have used one thing in particular that we haven't mentioned, which is that the roots are distinct. Okay, we'll deal with the case when they're not distinct in a second. But notice that this is irrespective of whether or not m1 and m2 are imaginary or real, right? M1 and M2 could be real or imaginary, right? And this will always be the solution. So what we can do to simplify our equations, to solve these equations much simpler, is we can assume that we know the solution, right? And once we assume that we know the solution, then we can find the solution much quicker. I'll show you what I mean by that in a second, right? But let's do a particular example, okay? So we can actually see how this is working. All right, so let's say we have the differential equation. Let me use something that I know factorizes. So let's do something like, let's see, x minus 3 times x plus 4 would give me, so d squared y dx squared. So that would be minus 7 dy dx. And then plus 12y equals 0. All right, so let's solve this differential equation. Let's do this the long way first, and then we'll do it the short way right afterwards, okay? I promise you that the short way is really, really easy. In fact, the methods for solving homogeneous differential equations of second order is actually much easier than solving first order, in my opinion. All right, so let's do this the long way first so we can understand the proof that we just did in the general case for the basic case, right, for the particular case. So we had initially started off by saying we can sort of pseudo factorize this. We're not exactly factorizing, right? But we can factorize this in the sense that we can write this as d by dx, this is squared, minus 7 d by dx plus 12 operating on y. Now, I've chose this equation, these coefficients, on purpose because it turns out that if you have x squared minus 7x plus 12, this can be written as x minus 3, x minus 4. Okay, I chose that on purpose. So that means that we can write this differential equation as d by dx minus, let's say 3 is the first one, doesn't have to be, and then d by dx minus 4. operating on y, right? We can write it like that. And so then we can say this whole thing here is omega. And so now we've simplified the equation to be d by dx minus 3 operating on omega equals 0, which we can expand as d omega dx minus 3 omega equals 0, which is separable. We can rewrite this as 1 over omega d omega dx equals 3. And so integrating both sides is going to give us natural log of w equals 3x plus c. Okay. And so we end up with omega equals, a to the power, or a times e to the power of 3x. This is the whole first slide that we did of the general solution, right? Everybody follow this so far to finding omega?
Yep.
Yes.
Okay. But now keep in mind that we also said omega was equal to dy dx minus 4y. So we just set those two things equal to each other, right? We have an expression for omega here, an expression for omega here. Let's set them equal to each other. So we now have, right, that dy dx minus 4y is actually just equal to a times e to the 3x. This is a non-separable, but this is a linear first order. So we can use an integrating factor here. Our integrating factor here is going to be mu x equals e to the power of the integral of minus 4 dx, okay, which is, of course, just e to the power of minus 4x. Remember that our c can be 0 here, so we make it 0, because why would we not? And then we can multiply the entire differential equation. It becomes e to the minus 4x dy by dx minus 4 e to the minus 4x y equals a e to the minus x, right? Okay. And so we can simplify the left-hand side. It's just product rule. This is d by dx.
Sir,
Yes.
why the one on the top? Oh, nothing.
Okay. So we have e to the minus 4x y equals a e to the minus x. And now we're in the position where we can take the integral of both sides. So we take the integral of both sides. And we end up with e to the minus 4xy equals, well, it's minus a e to the minus x plus b, right? This is just just using b instead of c, right? Just so that it's a and b. But instead of using minus a, remember that a is an arbitrary constant, so we're going to rename that just regular old a. Okay. And so we have that finally, if we divide both sides by e to the minus 4x, or multiply both sides by e to the positive 4x, we end up with y equals a e to the 3x plus b e to the 4x, just as we wanted.
Where did the minus 4 e to the power of minus 4xy go?
Huh?
How can I explain this? Do you see the line where it says e to the power of minus 4x dy dx minus 4e to the power?
Yeah.
Okay, so
On the right-hand side?
like I get that you factor out the d over dx, right?
Mm-hmm.
But where did the minus 4e to the power of minus 4xy go?
It's product rule. Remember, this is what we did like 3 days ago when we're doing
you're
product rule.
putting it in the product.
Yeah.
Makes sense. Okay.
Got it?
I think I understand everything instead of this part where when we were doing this 3 days ago. Have you already uploaded the videos of the?
No, I haven't. I'll upload them after we're done today.
Okay, sorry, because I just understand this part and I don't know, like everything before was okay, but here I just don't.
All
don't even
we're
imagine how to
doing
solve it.
all we're doing is we're recognizing that this right here, this whole thing is equal to that thing in brackets. That's the only like trick here at all. So we just recognize that that's the thing in brackets and we can write it much simpler. And if we can write it as one derivative, we can take the integral of a derivative, no problem.
Sir,
Yes.
may we be asked to find A and B?
Yes. Oh yeah, absolutely. We'll get to the
And
initial
would-
conditions in a second.
Okay.
What were you gonna ask though?
Like, would they have to give you 2 points and you'd have to
Yes.
do simultaneous equations?
But they usually won't give you 2 points. What they'll usually tell you is the value of the function at a point and the value of the derivative at that same point, or maybe at a different point. I'll show you that later. That's a good question, right? You absolutely will. What we found here, just to keep ourselves in check with our terminology, this is a general solution. It's not a particular solution.
So b is just another constant.
A and B are just random constants, right? Remember that
Yeah.
B came from an integral, and so did A. Both A
Yeah.
and B came from integrals, so they're just
Sure.
like plus C's.
But remember you told us, so we got a negative A, but then you said remove the negative sign because
Yeah.
A is an arbitrary.
Uh-huh.
What does like arbitrary mean? Like
Arbitrary means it can be anything.
anything. Okay.
Depending
so we
on
don't
the situation,
know.
it could be, -1 or 1. And it doesn't matter if you'd let A be the same as minus A,
Okay.
or you change it to minus A, then when you plug in your initial conditions, you'll just get negative of what you would have gotten regardless. So just to make it look nicer, we just use A and B, right?
Okay.
Make sense? Okay, so let me show you the easy way, right? Although this is not that hard, right? It's not that many lines. If you just memorize this process, this will work. But there's a much easier way of doing it, right? So the easier way of doing it is to assume, since we've already done the general case, we're going to assume we know the solution, all right? And once we assume that we know the solution, we're good to go, right? So if we assume that we know the solution, let's take the exact same differential equation, which was d squared y dx squared minus 7 dy dx plus 12y equals 0. Let's assume that the form of the solution is, y equals e to the power of mx, right? And so I know that I'm not technically writing out both solutions. It turns out that it actually doesn't matter, because what we're going to see is we end up with, if we assume this to be the form of the solution, we end up with 2 possible answers. And what we're going to say is that anytime we have multiple answers to a differential equation, if it's linear, the general solution will be the sum of those solutions. And I'll show you that in just 1 second. All right. So for right now, bear with me. Huh?
Is that because either A or B can be equal to 0?
Either A or B can be. What do you mean?
Like if you sum them together, like both possible solutions?
Oh, yeah, that's exactly why, right? So yeah, that's exactly right. What we're going to see is that if we have 2 solutions to the homogeneous equation, if we plug the sum of them into the differential equation, we end up with 0 again. So that's got to be the more general solution, right? That's exactly right, if I'm understanding you correctly. Okay, so if we assume that this is the solution, or it's the form of the solution, right? That's a very vague term, right? If we assume that this is the form of the solution, then we can just say, all right, let's plug it in and see what happens, right? Let's plug this in. If we plug it in, we end up with, well, we need to find the first derivative, right? What's the first derivative of that thing? Well, what is it?
M times e to the power of mx.
Good. M e to the mx. What's the second derivative?
M squared times e to the power of mx.
Awesome. And so if we plug those things into the differential equation, we end up with m squared e to the mx plus, or minus 7m e to the mx plus 12 e to the mx, right? That's what y is, equals 0. Well, guess what? Everything here has a factor of e to the mx in it. So let's get rid of that factor, right? So we can just divide both sides by e to the mx, and we end up with the equation m squared minus 7m plus 12 equals 0. This right here is called the auxiliary equation. Auxiliary, I didn't spell that right, equation. So every first or every second order, actually every nth order degree ordinary differential equation with constant coefficients that's homogeneous will have a corresponding auxiliary equation, right? This auxiliary equation is literally just the quadratic that you would form, or the parabola, or the polynomial that you would form by replacing y with 1, replacing dy dx with x, replacing d squared y dx squared with x squared, replacing d cubed y dx cubed with x cubed, and so on and so forth, right? And so once we've got this quadratic, we can easily find what the only 2 possibilities for m are, right? This tells us that m can either equal 3 or m, so we'll call m1 3, and m2 can be 4. Then all we have to do is remember the result from the general solution. The result from the general solution basically tells us, right? So I'm going to specify for real solutions right now because we're going to slightly alter it for imaginary solutions, but we'll get there in a second, right? So it tells us that for any solution to the original equation, I'll go back to it, we know that the general solution is just going to be a constant times e to the power of one root, x, plus a constant times e to the power of the other root times x. Keep in mind that m1 and m2 in this original equation and this original solution are precisely the roots of the auxiliary equation of our differential equation. So we can immediately now, pretty much immediately in this step, we can write down that the general solution is just y equals a e to the 3x plus b e to the 4x. Okay? That's it. That's all we have to do to solve this differential equation. All right? Does that make some sort of sense?
It does.
Good.
So, sir, one question. Does this step have to be done with the general solution? So do we have to know the general solution in order to do this step, like this method?
Yeah, I mean, no. Okay, so you can conceive of another way of formulating the solution. Now, it won't be a proof, right? So you can conceive of another way of doing the solution by looking at the first example that we looked at yesterday, which was d squared y dx squared equals y. I think it was the one that we did. And what you get from that is by just sort of making an educated guess, you say, well, a solution to that is e to the x, right? Or e to the mx if there's a coefficient in front of m. Because what function's second derivative is equal to a constant times itself? Well, e to the x is a pretty good guess. And so you would guess not necessarily e to the x, but e to the mx, and then you could carry through with this exact same solution, right? But you would end up with, two different possibilities for m. And so you'd say, okay, so one solution, so you say like one solution could be something like e to the 3x, right? This is one solution. And you could say another solution would be something like e to the 4x. Okay, interesting. And you could say, all right, well, if I just put a constant in front of each one, let's see what happens when I plug a constant into constant multiple of e to the 3x into the differential equation. Well, I'd have dy1 dx is just equal to 3a e to the 3x, and d squared y1 dx squared is just equal to 9a e to the 3x. If I plug these into the differential equation, I end up with 9a e to the 3x minus 7 times 3a e to the 3x, and then plus 12 times a e to the 3x. Let's see what happens when we simplify this. Well, we get 9a minus 21a. This should be a 21a. Plus 12a, right? All times e to the 3x. This is in fact equal to 0. Okay, that's good. So that solution works. Fair enough. Same thing is going to happen if we plug d squared y2 dx squared. I'm not going to do all the algebra this time. Minus 7 dy2 dx, right? Plus 12y2. This is also going to give us 0. So we'd say like check, check. Those both work. Well, interestingly, or if we put an a here or b, that's also going to work. So what happens if we combine the two? Well, we could say let y equal y1 plus y2, right? So let's actually do this on a separate page because this is a really, really important concept. This is going to end up being our general solution, right? The thing that I just boxed, right? And I'll show you why. So say we have any differential equation that's of this form, right? So we'll say any.
Sorry, can you go back like to the third slide real quick?
The third slide?
Yeah.
Sure.
I'll quickly just. Okay, got it. Thank you.
Awesome. All right, so let's see what happens. This is a really, really interesting or important concept. It's crucial for the next thing that we have to learn, right? But we're staying on this topic for a second. Don't worry, I'm not moving forward, but this is a crucial thing, right, for differential equations. So say we have any second order differential equation that's homogeneous, linear, and got constant coefficients, right? We now know that's a really fancy term for just saying a d squared y dx squared plus b dy dx plus cy equals 0, okay? And say we have any two solutions to this differential equation. Any two solutions at all. right? Doesn't matter what the form is, doesn't matter anything. We have two solutions. So we'll say y1 and y2 are two solutions to this differential equation, right? So if they're both solutions, let's take a look at what happens when we let, we'll say like y, just regular old y, equal y1 plus y2. What happens if we take their sum? If we have any two solutions and we take their sum, what we're going to see is that we get another solution, but let's prove it. So if we have the sum of solutions and we plug this into our differential equation, what do we get? Well, we would get the first derivative of y is just the first derivative of y1 plus the first derivative of y2. And the second derivative of y is also just the second derivative of y1 plus the second derivative of y2. All right, fair enough. So let's plug these things into the differential equation. We're going to get a times d squared y1 dx squared plus d squared y2 dx squared plus b times dy1 dx plus dy2 dx and plus c times, well, y1 plus y2. All right. We don't know that this is equal to 0 yet. We're about to show that it equals 0. Okay. So what we're going to do now is we're going to gather all the y1 terms and all the y2 terms. All right. So if we gather those terms, we'd end up with, so this is equal to a d squared y1 dx squared plus b dy1 dx plus cy1, that's in one set of brackets. And then the d2 terms, or the y2 terms, are going to be a d squared y2 dx squared plus b dy2 dx plus cy2. But guess what? y1 and y2 are solutions to this differential equation, which means when we plug them into the differential equation, we better get 0. So that means that this will be 0 and this will be 0. And not surprisingly here, we end up with a solution equal to 0 as well. And so what this tells us is that y itself, y, which is a sum of y1 and y2, gives us another solution. All right? Does that make sense? We could correspondingly say that if we had y1, y2, and y3 that are all solutions, we could add all three of those, and that would be another solution. We could do the same thing with 4. The only thing, hold on, I think I'm going to answer your question. The only thing is that with second order differential equations, we're only going to get 2 solutions, right? With third order differential equations, we'll get 3. With fourth order differential equations, we'll get 4. We're not going to do those, but you get the same amount of solutions as the highest degree derivative, okay? In this case, our highest degree derivative is 2. We're only going to get 2 solutions. Now, we're not going to prove that there are only 2 solutions, although we did show using the factoring method that 2 solutions naturally come out, right? And we don't get any more. All right? So using this idea, you could say, assume the form, I'll go back and forth, so don't worry about me going back. So you could assume the form is e to the mx, here we go. We plug it in, we show that we get 2 different possible solutions, and so we say that the general solution is just the sum of those 2 possible solutions. All right. But the unsatisfying thing about this method is that you already need to know that the form is e to the mx. All right. Whereas the other method, you don't need to assume anything. You can just solve it straight. All right. Okay. So what I want to do now is I want to classify the possible solutions, because that's the other really important thing. And it's a little surprising, actually.
We're going to be covering the cosine and sine form today as well, right?
Yes, yeah, that's part of the classification, right? So as far as we've seen what we've seen so far in a particular example is only when the 2 roots are real. But of course, we have an auxiliary equation, which is a quadratic. We've now studied complex numbers sufficiently to know that quadratics often have complex roots. And in fact, they don't just have complex roots, but sometimes they have repeated roots, right? So you have b squared minus 4ac is equal to 0. You get the same root 2 times, right? Those are actually surprisingly, might be kind of surprising to see, that those actually both are going to yield 2 different possible solutions, right? So let's do that right now. So we know what we've developed right now for sure is that when there are 2 distinct roots, so for any 2 distinct roots, so we'll say if we have, this thing right here, plus b dy dx plus cy with auxiliary equation. So I say with aux equation given by, a m squared plus bm plus c equals 0, right? We'll say where the solutions m1 and m2 are distinct. So this means two things, right? So this means, so I'll say like i.e. b squared minus 4ac is not 0. All right. This could mean positive or negative, right? But it's not equal to 0. So in other words, if this is our setup, if we have all these things, so if we have a differential equation that's second order with constant coefficients, it's homogeneous, right? And we have an auxiliary equation to that differential equation given by am squared plus bm plus c, and the solutions or the roots to that equation are m1 and m2 and they're distinct from each other, then we can definitely say then the general solution to our ODE, or our diffeq, will be y equals a e to the m1x plus b e to the m2x, okay? However, there are two possibilities for b squared minus 4ac not equaling 0, right? One of them is that b squared minus 4ac is positive, in which case m1 and m2 are real. And the other possibility is that b squared minus 4ac is negative, in which case m1 and m2 are complex. All right, so let's deal with those two classifications. We'll say case 1.
So what about repeated roots?
We'll get there. That's a separate case altogether because it's kind of surprising. So case 1, we're going to have, b squared minus 4ac is positive. Right? This tells us that m1 does not equal m2, right? And they're both real. So if they're both real, the solution's easy. It's trivial, right? So in this case, we have the exact same thing. I'm not going to even change anything here. Okay? Fair enough? Nothing interesting here. Nothing new. So if they're both real, we get the exact same thing. We don't have to worry about it at all. Okay? If they're both complex, what can we say about their relationship to each other? How are M1 and M2 going to be related if they're both complex?
Complex conjugates?
They're going to be complex conjugates of each other. That's excellent. Good. So if the discriminant is less than 0, this tells us immediately that M1 and M2 are not the same thing, right? They're not the same thing, but they're both complex, right? And since they must be complex conjugates of each other, we can write them in the following way. We can write this as M1 equals, let's say, alpha plus I beta, and M2 equals alpha minus I beta. Okay? That has to be the case. Remember that we know this from FP1 even, that if the solution to a quadratic or the solution to a polynomial is complex, then its complex conjugate must also be a solution, right? So if there's only two possible roots here, and one of them is complex, the other one must be its complex conjugate, okay? So we have M1 and M2 are equal to this, right? And again, the solution is exactly the same as before. So the general solution is a e to the, alpha plus I beta x, and then b e to the alpha minus I beta x. There's no subtlety here. Although what we typically do, it's much easier to see this, it's much nicer looking, is we write this in the form a e to the alpha x e to the I beta x plus b e to the alpha x e to the minus I beta x. It should be I beta x. Both terms have an e to the alpha x in them, so we can factor that out. So we can write this as e to the alpha x times a e to the I beta x plus b e to the minus I beta x. And now what we can do is we can use Euler's formula. Euler's formula tells us that there's a relationship between e to the I theta and cosine and sine. So we can write this as e to the alpha x times A, and then in brackets cosine of beta x plus I sine B cosine of beta x, should be, I guess, in brackets, minus I sine of beta x, sine of beta x. All right, and then we can combine the cosine terms and combine the sine terms. But what we're gonna get, and if me just saying this is too many mental steps, I will do it all by hand. But I'm kind of running out of room here, so I'll just try and explain it verbally. And if you guys don't get it, I'll definitely go through it, so don't worry. But what we're gonna end up getting is if we combine the cosine terms, we'll have a plus b cosine, right? And then if we combine the sine terms, we'll have ai minus IB, or AI minus BI in front of sine. And we can just rename those A and B, right? So what we'll end up with here is that our solution is just of the form e to the alpha x, A cosine of x, or beta x, sorry, plus B sine of beta x. Where again, we have to be careful that we've renamed A and B. Okay. I'm not being super careful there because we only care about the final result. We don't care about the intermediary steps, okay? But just the whole point of this is that when we've got complex solutions, right? When we have our complex roots to our polynomial, to our quadratic in this particular case, we can naturally write this as cosine and sine times some exponential, right? So times e to the alpha x as well. All right. So this is a full classification, a fully done, completed classification of the solutions to second order linear differential equations with constant coefficients that are homogeneous, right, or homogeneous, with the roots of the auxiliary equation being distinct. Okay, so if M1 is not equal to M2, this is a full classification of the solutions. All right, does that make sense so far?
Yeah.
Any issues with the last line of algebra that I did there?
Yes, so that A kind of like A is equal to A plus B and B is equal to A minus B, right?
With an I. The second one would be with I multiplied in it as well.
Oh,
Yeah.
so,
A minus BI would be
so
B.
B is complex?
Could be. It could be, but remember that it's an arbitrary constant. So all we have to do is fit it to our initial conditions.
Sir, could you explain the last step again?
Of course. Yeah. Of course I could. So I'll do this on a separate page just so I have more room. So we started off by saying it's equivalent to just look at what happens to e to the I beta x plus b e to the minus I beta x, right? And what I'll do to make our explanation a little bit less tricky is I'll just give these like a subscript. I'll call these 1, okay? Because that way when we rename, we don't have to let like a times 3 equal a, right? We can actually name it something new. That b has a subscript of 1, it's just lagging. There we go. So we can write Euler's formula. Euler's formula tells us this is a times cosine of beta x plus I sine of beta x. And then it tells us, oh, that's a sub 1, right? And it should be, then we can also write the next term the same way, right? So we can use Euler's formula again. Oops, that should be a cosine of beta x minus I sine beta x. Okay? And so what we can do is we can combine the cosine terms. If we combine the cosine terms, we let a1 plus b1, that's going to be multiplied by cosine of beta x, right? And similarly with the sine terms, we can have, a1i minus, that should be a minus b1, not beta, but b1i times sine of beta x. Do you agree so far? All I've done is some algebra, and I've used Euler's formula. Good with that part?
Yep.
Okay, so then what we do is we just say let a1 plus b1 equal a, and let a1i minus b1i just equal b. And we end up with, this is the same thing as writing a cosine of bx plus b cosine of beta x.
It doesn't matter if you would say that A1 plus B1 is equal to B and I minus BI is equal to A, right?
No, it wouldn't matter at all. They're arbitrary constants, right?
Right.
We're gonna end up fitting those constants to our initial conditions to find a particular solution anyway, right? And so Fernando asked a good question because he said it looks like B is complex, and so it does, right? Sure, it looks like B is complex unless A1 and B1 are complex themselves, in which case the complex part would get, or imaginary themselves, in which case that would cancel out, right? And you could
Okay.
imagine a case where the sum of the complex numbers cancels out the imaginary parts, right? So the sum, so A itself could also be real, right? And in fact, for all of our equations, our constants A and B will be real, right? Okay, but certainly there could be cases where A and B are imaginary. We won't have them on FP2. But of course they could be. Yeah, there's nothing wrong with that. Remember, at the end of the day, these are just like algebraic, or these are just solutions to equations. So solutions to equations we know are very limited if we don't include the possibility of them being imaginary, right? Okay, so let's do an example of a situation where we get imaginary roots, okay? Because, it's all well and good to do this classification with random integers like this, or random variables A and B, so on and so forth, but it's obviously much helpful to see how this works in practice. So let's come up with a nice equation.
Sir, in the result, alpha straight up disappears?
No. There would be an e to the alpha x here. The only thing is that I said the only part that we needed to do, right, to show this last step here that Anastasia was confused about, was just show that the stuff on the inside is equal, right? Because we just carried an e to the alpha x all the way through. Does that make sense?
So it's that what we just done multiplied by that.
Exactly. I mean, this page that I'm on right now, this is the classification of the solutions to homogeneous second order differential equations with constant coefficients that is linear. I say it a different way every time. With the two roots to the auxiliary equation being distinct. This page gives you all that information. The next page shows you that last line of algebra only. Okay, so I'll say that this is the last, just in case you guys look back through this afterwards, this is the last line of algebra on previous page.
But this line was also multiplied by e to the power of alpha x, right?
Yeah, so our solution should actually be, is actually, y equals e to the alpha x times a cosine of beta x plus b sine of beta x. Yeah, absolutely. All right, let's do a situation where we actually solve this, right? So let's see. Let's come up with a differential equation that's got imaginary roots that are reasonable. So I guess we just need to come up with b squared minus 4ac is less than 0. So I'll just go ahead and start writing. So we'll say d squared y dx squared. Let's do like a minus dy dx. Hopefully the numbers don't come out too disgusting, but it's fine because we have a pretty easy solution to this, and we just need to make a big C. So we'll do like plus 4. Right, this should give us imaginary roots. So we can immediately write down, we don't even have to assume the form anymore. We can immediately find the auxiliary equation, because the auxiliary equation, so the aux equation, is literally just the exact same equation, but without derivatives, we just put an m, right? So the auxiliary equation is literally just m squared minus m plus 4 equals 0. And all we need to do is find out what the roots are to this polynomial, right? The roots here, of course, we would use the quadratic formula. So we'd say the m's are negative b plus or minus the square root of b squared, which is just 1, minus 16, good, over 2a. So this is just, we have two solutions. We'll say m1 is just equal to 1/2 plus root 15i over 2. And m2, stop me if I get any algebra wrong, is just 1/2 minus root 15 over 2i, right? There we go, complex conjugates of each other. That's nice. And guess what? It's as easy as just remembering the form of the differential equation. We have alpha alpha is just equal to 1/2, beta is just equal to root 15 over 2. And so we can say confidently now that the general solution is just some constant multiple times e to the power of 1/2 x, right? And then brackets cosine of root 15 over 2x plus, oh, sorry, there should not be brackets there.
Sir, like
Yeah.
when you found the roots, you said like complex conjugate of each other. That's nice, as if you were surprised. Like
No.
it's like compulsory, right?
It is, yeah. You can
okay,
prove. Yeah.
yeah.
No, I'm
Sorry.
saying like just recognize that what we said before wasn't BS, right? It's actually true. And you can see that as evidence here, right? All right, so then we have B sine. I got the original form written a little bit incorrectly, but this is the correct form. There we go. That's our general solution. That's it. We're done. We've solved the equation. This is true. This is complete. This is the full solution. We've already done all the hard work to get to this point. This is it. We've just solved the homogeneous part of this differential. Don't ignore that terminology. That'll come later. We've just solved the homogeneous differential equation. It's solved. Okay. We can verify this. So this is another thing that's really nice about differential equations, is that whenever you have a general solution, you can verify to see if it works, right? It's kind of a pain, but you can do it. So you can find, to check, we'll say, to check, just calculate dy dx and d squared y dx squared, right? And plug in. Right? If it gives you 0, you're good. If it doesn't give you 0, you've done something wrong, right? So if you're not fully confident in what you've done, you can always check, all right? So this is, I mean, yeah, we've done a lot of work up until this point, but we have to be really appreciative of the fact that our work led us to a complete solution. And in fact, it's going to lead us to an even more complete general classification of all solutions. And so all we have to do is use that result, and we're done. We're done with the equation. We don't
I actually like this chapter more than I like second more than first.
I know, it's strange. You'd think, I mean, because in general second order, I will say this, in general second order is much more difficult. But this particular class of second order, we just solved all of them. We solved all of them. I mean, that's not true. We didn't solve the case where M1 is equal to M2. There's a slight surprising thing that happens there. Okay, so, but everything okay up until now? I mean, we haven't done anything with particular solutions. What I want to do is I want to do the classification for when M1 is equal to M2, and then I'd like to do some past paper questions. And the past paper questions almost always have particular solutions, initial conditions in there as well. So that we'll get there. Okay, so everybody okay with this though?
Yep.
Awesome.
Yep.
Awesome. All right, so the case for when M1 is equal to M2. Interesting. It's an interesting case. So what happens in the degenerate case, right? So when M1 is equal to M2. It's actually kind of cool what happens here. I like it a lot. So here's what we're going to do. We're going to repeat. I'm sorry for the rotation. It's lagged diagonally. Okay, so we're going to repeat the process that we did before, right? The factoring process, but we're going to do it. I'll do it with a particular one because I think it's easier to follow when you use like actual specific numbers. But just know that this exact same thing would carry forward if you did the general solution, right? With A, B, and C. I'm not going to use A, B, and C. I'm going to use particular numbers, like I said. But this exact same thing could be repeated with A, B, and C, and it would be a good exercise actually for you guys to try it, right? All right, so we're just going to use a particular polynomial that's got repeated roots. So the typical one to do is like x plus 1 squared, right? So that's just x squared plus 2x plus 1. So we're going to say, let's solve the differential equation d squared y dx squared plus 2 dy dx plus y equals 0. Yes?
Could M1 and M2 be complex? Could they be complex numbers?
If they're the same?
Yes.
No, because they have to be complex conjugates of each other.
Oh, yeah, that's true.
Right? So no, they couldn't. All right. So, yeah, so that's a good point, right? So no matter what happens here, M is going to be real. Yeah, that's true. That's a good observation, right? All right, so what we can do here, if we're doing it the long way, is we can say, we write this as d by dx plus 1 times d by dx plus 1 y, right? So this is the long way, remember. This is not the kind of thing that you have to do on the exam. This is just the long way. It's going to lead us to our classification, all right? Okay, so we've got our factorized form. We called this omega. I know this is kind of a pain to reproduce. And so we end up with, sorry, my mic is kind of far away. I don't know if you guys can hear me. So we end up with omega equals dy by dx plus y, right? And we end up with the other differential equation, d by dx plus 1 of omega is equal to 0, which we can solve, of course. This is d omega dx plus omega equals 0. Separable. So let's separate this. This is going to give us 1 over y d omega dx equals minus 1. Integrating gives us that, I'll just jump to the solution here. Our omega is going to be e to the minus x plus c. So we can write that as just a e to the minus x. Okay. So far, so good?
Yes.
Uh-huh.
Okie doke. So then setting omega and omega equal to each other, we end up with a e to the minus x equals dy dx plus y. We again are going to just use integrating factors here. So our mu is just e to the power of the integral of the thing that comes in front of y, which in this case is just 1. So our mu is just e to the x. Okay. Nice. So if we multiply the entire thing by e to the x, what do we get? Well, we get on the left, I'm going to reverse the side. So we get e to the x dy dx plus e to the xy. But interestingly now, on the other side of the equation, we just get the number a, right? Whatever a is. It's just a constant. So the e to the x and the e to the minus x cancel each other out. This is always going to happen. So imagine if I just replaced, 1, the number 1 in my initial factorizing, right? And imagine if that 1 was replaced with any other number. No matter what number you replace that with, you're going to end up with omega is equal to a times e to the minus whatever, that number is times x. And then your integrating factor is always going to be e to the power of the positive, whatever that number is, times x. And so when you multiply through, they're always going to give you a constant, which is interesting now, right? And I'll show you why it's interesting. So the left-hand side is still product rule. This is still product rule. This is still going to be d by dx e to the x times y. And the right-hand side is just a. But now when we integrate, interestingly enough, when we integrate, we get e to the xy equals ax plus b, right? So we have a linear equation now on the right-hand side. We get an extra x that we wouldn't have gotten there if there had still been a leftover e, right? But since there were no leftover e's, the integral of just a constant is just that constant times x plus c, right? In this case, we're using b. So now if we divide both sides by e to the x, we get y equals ax e to the x, a to the e to the minus x, plus b e to the minus x. So in other words, we still get something that sort of looks like, a e to the m1x, b e to the m2x. In this case, our m1s and m2s are the same. They're both minus 1, but one of the terms has an extra x factor, okay? This is kind of strange that this happens, but this is true. This will always happen. And so we can generalize now our third classification to the solution. So we can say,
So would it also work if we just used the distinct solution and made them equal to each other and work with that?
No. So if you use the other solution, what you're not accounting for is the fact that m1 minus m2. So I'll show you. I'll go back to our original derivation. So in our original derivation, where was it? It was here. Nope, it was here. Okay, so actually, this is nice. I have it circled. It's lagging a bit, but I've got the term. That term that's circled there, a over m1 minus m2, right? That would make no sense if m1 and m2 were the same, right? We actually secretly used the assumption that m1 and m2 were different because you can't divide by 0, right? So if m1 and m2 are the same number, that term right there doesn't make any sense. And in fact, not only that, but e to the m1 minus m2 would be constant. It would be 1, right? So this derivation here was secretly using the fact that M1 and M2 were different. They don't have to be, one greater than the other, or they don't have to both be imaginary. They don't have to both be real, but they have to be different. Otherwise, this derivation doesn't work. So that general solution here, a e to the m1x plus b to e to the m2x, only works if m1 and m2 are different. All right? Make sense?
Yes.
Okay. So but now we've solved the third possibility, right? So I'll write down all the possibilities on the same page. So we have them in one nice, concise place. And then we'll do some exam papers. Or some past paper questions. All right, so we have 3 possibilities, right? So the first possibility, case 1, is that b squared minus 4ac is greater than 0, in which case we have really uninteresting stuff. We just have y equals a e to the m1x plus b e to the m2x. Okay, so I guess I should say auxiliary equation is this thingy, right? So with solutions, m1 and m2. All right. So that's our first case. Easy peasy. Our second case, case 2, we have b squared minus 4ac is less than 0. We have, this tells us that we have m1 is alpha plus beta I beta, and m2 is alpha minus I beta. And furthermore, it tells us that our general solution is e to the alpha x times brackets a cosine of beta x plus b sine of beta x. And then, so that's our general solution. And then case 3, which we just showed, is that b squared minus 4ac is equal to 0. In which case we have, m1 equals m2. And so we can just call them both m, right? No, we'll call them both m1, right? Doesn't matter. Choose one of them. Then our general solution is always going to be of the form. Now, I did my x on A, but I think in your book they do it on B. So we'll always write this as A plus bx times e to the m1x. Okay? If you look back on the previous page, that's exactly what we had, right? We had e to the minus x. I know it's lagging. But we had an ax plus b. In this case, just to keep it consistent with what your book says, I'm doing a plus bx, right? Doesn't matter because they're arbitrary constants anyway, right? Laggy. Come on. There we go. All right, so this is the full classification. This is every solution to every second order linear differential equation with constant coefficients that's homogeneous.
Could you go back a slide, please?
Yes.
Okay.
This one? Well, yeah, this one.
Yes.
So while you're doing that, I'm going to start pulling up some past paper questions.
So I'm gonna quickly go and drink water.
Go for it.
Okay, so
Actually.
got it.
Cool. All right, so I'm going to find a good second order. Not that one. Not that one either. These are all non-homogeneous. So of course, not as nice. Ugh, they're all non-homogeneous. I guess we can follow the first part of one. Okay, so we'll do this one. I'm altering it ever so slightly to make it so that we can do it. Fernando, are you back? Actually, make a new presentation. We'll give Fernando a minute or so. Well, I'll go ahead and write down the problem. All right, so this, just to keep in mind, guys, I'm doing an altered version of June 2009, question 8. I'm doing an altered version because we don't have the skills necessary to do the full version yet, but we'll get there. Okay, I promise. So they have a non-homogeneous equation. We're doing a homogeneous equation. Okay, so we're going to solve. We're going to find x of t, given that we have d squared x dt squared. What is it? 5 and 6, right? Plus 5 dx dt plus 6x equals 0. Okay. And we also have some initial conditions, right? So they also tell us that x is equal to 0, and dx dt is equal to 0 at t equals 0. This is a very common initial condition. So, Alex, I think it was you who pointed out that, or maybe it was Javier, I can't remember, it doesn't matter, who pointed out that we have two constants, a and b, in our solutions, and so we need 2 points to find a and b, but often it's much more convenient to not know 2 points, but rather something like the initial position and speed, right? At time
It was
equals
100% not me.
Okay. Well, I couldn't remember. And it was one of the two of you. I knew that much, right? So we're going to use, in this particular equation, you can think of it actually, and some of you physicsy people might really like this interpretation. The harmonic oscillator is going to obey a second order differential equation like this, just like this, right? And so we can think it.
Always roast me for the fact that I dropped physics.
I know. That's okay. You can still appreciate a good harmonic oscillator problem, right? So you can imagine that this equation describes the motion of a spring that's moving back and forth, right? And what we're doing, instead of specifying 2 positions that the spring passes through, we're specifying the initial position and initial speed, right? So, and that's going to be good enough to solve the particular solution here. But keep in mind that if we only had x equals 0 at t equals 0, we're not going to be able to find our constants. Okay, we will not be able to find the full description of motion here.
So are we going to use differential equations in M2?
No, unfortunately. There's differential equations in M3, not in M2. I know, it's a shame.
Changing differential equations in physics for decision 1.
Huh? What?
We changed differential equations in physics for D1.
Yeah, I mean that's one of the things that I love about M3. It's just like it ties all of the techniques that you learn from your further math modules and applies it for the first time to like a real world scenario to physics. The issue, and this is a legitimate issue, is that it's really hard. It is actually pretty hard. I mean, it's a shame for me because it's like my favorite well, it's not my favorite module. It's one of my favorite modules, but it is pretty hard. So I understand the decision to not do it. But anyway, all right, back to this. So we have this differential equation. This is pretty straightforward, right? So I will say that the first thing that you want to do when you approach a differential equation just like this. Oh, Fernando, you weren't here, I don't think. I was saying I'm doing a modified version of this problem. So if you're actually looking at the questions by topic, you'll notice that they don't have it equal to 0. They have it equal to something else. And since we don't have the skills necessary to do that yet, we're making it homogeneous. Exactly. Right? All right. So the first thing that we want to do whenever we're approaching a second order differential equation that's homogeneous, we want to find the auxiliary equation, right? The auxiliary equation in this case is just the quadratic. So we would just write this down as m squared plus 5m plus 6 equals 0. And we want to find our solutions to this auxiliary equation, right? So the solutions would be m1 and m2. And this is easy, right? This is just doing quadratic formula, right? So we'll say m1 comma m2 equals -5 plus or minus the square root of 5 squared, so 25, minus 4 times a times c, well, that's nice, over 2, right? So we're going to have m1 equals -5 plus 1, so -4 over 2 is -2, and m2, does this factorize? It factorizes, oh my god.
Yeah, that's why I was like, what is happening?
I just defaulted the quadratic formula. Didn't even check to see that this factorized.
That's
Okay,
not fair. He starts with calculator, and I'm like,
Yeah.
what?
Don't be me. Don't be Fernando. Factorize this.
So,
if you can factorize it, no, you can be
so,
Fernando if you want.
why
Yeah.
wouldn't you wouldn't here using the omega form be easier because you have the first derivative, so you can get one constant first and then get the other constant?
Oh, sure. Yeah. Yeah. To find the particular solution. Yeah, maybe. Yeah.
Yes.
But I'll say this much. I would be hesitant to use the omega version on the exam. And this is going to sound really condescending, but honestly, I don't trust the Edexcel examiners to even understand what you're doing when you do that. So I wouldn't use the omega formula just for your own sake, right? It is the more like proof approach, but just use this for your own safety, right? Okay, so this can be written as m plus 2, m plus 3. I don't know why I use the quadratic formula. In any case, we end up with m1 is equal to minus 2, m2 is equal to minus 3. All right, and so we have two distinct real roots. We can immediately, without even thinking, we can be robots, and we can just say this is a e to the minus 2x plus b e to the minus 3x. That's our solution. But of course, we want to find our
Use x and t.
Oh, thank you. Yep, it should be t, a e to the minus 2t plus b e to the minus 3t. Right?
And instead of yx, right?
Yes. Okay, maybe you need to think a little bit. I said without thinking, maybe it's just me who doesn't think. Yes, you're right. It should be x. I hate that. If I don't get the eraser size like perfectly right, it just erases everything that I do. It's really, really frustrating. All right, there we go. So that's our x of t. Now, of course, we want to find our initial conditions. We need to find our a and b. So we're going to plug in our initial conditions. So we're going to say x of 0 equals 0, right? So if we plug in 0 into our equation, we just get a plus b, right? Not too bad. And then we also know that x prime, right? X prime of t, or dx dt, if we actually take the derivative here, dx dt, not dx dx. Dx dt is just minus 2a e to the minus 2t plus or minus 3b times e to the minus 3t. We've got to be careful that we don't do renaming here, right? You can't rename here because this is the same a and b as in your first equation, right? So don't rename. Minus 2a is not a here, okay? So if we plug in 0, so dx dt of 0, so at t is equal to 0, is just minus 2a minus 3b, and this is all supposed to equal 0, okay? Well, guess what? No surprise here. We get two equations with two unknowns. We can solve this, okay? So we're solving the equations a plus b equals 0 and minus 2a minus 3b is equal to 0. We don't have to even like combine these equations in any particular way. Substitution is really easy. So this first one tells us that a is equal to minus b, and we can plug this in here. I guess we can plug it into that part. We get, so 2b minus 3b equals 0, right? This tells us that b equals, what did I do? Did I copy the problem? Oh, it's that I copied the problem done wrong. This is supposed to be 2. That was supposed to be 2. It's going to say, did they just give us a differential equation where the solution is 0? That would be very frustrating. It's supposed to be 2 there. Okay, so then we get minus 2b, 2b minus 3b is equal to 2, right? So in other words, minus b equals 2, b equals minus 2, a equals positive 2. And so we end up with a particular solution, x of t equals 2e to the minus 2t minus 2e to the minus 3t. Done. Make sense?
So it's much simpler to solve it this way, right?
Oh, yeah. Much simpler. Much simpler, right? You don't have to reinvent the wheel. Once it's already invented, learn it so that you can maybe apply that thing to other situations, but you don't have to repeat the omega process anymore at all, right? This is always going to work. And of course, this is a case where the two roots are distinct and real, and I think that maybe that's the easiest case, but you can also just learn the classifications, right? There's only 3 classifications. There's not that much to learn, right? So you just learn that it's a e to the m1x plus b e to the m2x when it's real and distinct. It's e to the alpha x times a cosine of beta x plus b sine of beta x when it's imaginary. And then it's just a plus xb e to the m1x when it's the same roots. Okay? That's it. That's it. We solved it. We've solved all of them. All right. Satisfying-ish?
Me, I thought this was going to be a lot harder.
Well, we have half the chapter left. Right?
Okay.
So this is not, you probably won't get on the exam just a homogeneous equation like this. Right? So I was just looking through the questions by topic for one of these, and I realized, there aren't any, because this is usually part A of a problem, or it's like part 1 of part A. Meaning, and I don't mean like they're like super long, I'm just saying to do a non-homogeneous equation, we're going to have to always do this, right? I'll show you that in a second, right? But we also have to deal with a more complicated version of this problem, right? The more complicated version of this problem would, of course, be like the second thing that we did when we were talking about separable differential equations, was like throw in a term there that makes it not separable anymore, right? It keeps it linear, but it's not separable. So in other words, we throw in an f of x, or we throw in a q of x in our first order case. Here we're going to throw in an f of x. So our question now is, what happens? So I'll say, like, what about things that look like this? So you still have linear second order constant coefficients ODE, right? But it's no longer homogeneous, right? Remember that our original generalized second order linear differential equation with constant coefficients had an f of x. And we only just studied the case where f of x is equal to 0. Okay? So what if f of x is something else? That's going to be a tiny bit more challenging. And I will say this much. I want to do a little bit of the omega process. I'm not going to do the general one because we end up with a double integral, and you guys do not know how to do double integrals, so we're not going to do that one. We're going to do it for like one specific case. Okay.
Are double integrals an integral after an integral?
Yes, but we have to change the variables. So we have to be integrating with respect to x prime and x. We have to do like an antiderivative integral notation. It's a mess. So I could sit here and explain it to you over the course of 20 minutes or so, but it's just as satisfying, I think, in a way, to show you a specific case and tell you how you can sort of use that specific case to help you solve other problems, right? It's going to lead us to a concept called particular integrals. But really quick, you guys are going to have to forgive me. You're going to have to give me 3 minutes. I'm just going to run to the restroom, okay? I'll be right back. I just want to mute my audio. I'll be right back. All right, everybody here?
Yup.
Okay, so before we dive into this, are there any questions? Any particular things that you want me to do again? You want to see another example, so on and so forth? Tell me, okay? We're going to be doing more examples, and the good thing about this next thing is that every time we solve one of these, we inherently have to solve one of the problems that we were just doing. So we have to solve a homogeneous equation as well. So we'll get practice with the homogeneous stuff. But if there's any conceptual problems, anything that you guys want to see in detail right now, please tell me before we move forward. Okay. All right. So perfect recall. So I should expect 100% on everybody. All right. All right. Let's go. So this is not that hard. What we're going to do is I'm going to talk about a particular case. Okay. let's do a particular example, and we'll see how we can maybe alter this example to do some more complicated ones. Okay, so well, actually, let's do a couple of steps in the general one, but then we're going to modify afterwards so that we don't have to do all of them, right? I want to show you that the same process that we had done before could actually lead us to the solution again. We just have to be a little bit more careful on how we do it, okay? So our original process was to start off by dividing everything by a, right? So we could just say, well, we could make a simplification and just say, what if we were trying to solve the differential equation, you know, this thing, right, equals f of x over a, right? Well, we could still do the same factorizing on the left-hand side. So we could still write this as like d by dx minus m1, and then d by dx minus m2y equals f of x over a. Okay? But now when we name this omega, and we're still going to name this omega, we end up with, so omega equals d by dx minus m2 operating on y, or in other words, it's dy dx minus m2y. But now we have the differential equation d by dx minus m1 omega equals f of x over a, and not 0. Before, this thing equaled 0, but now we got a differential equation d omega by dx minus m1 omega equals f of x over a. And so this is a solvable differential equation. There's no problem solving this differential equation. However, it's not separable, right? So if you remember before, in our first derivation, we did this exact same thing, but we ended up with 0 here. And this first equation, this first order, was separable. But now we would have to use integrating factors, right? So to solve this differential equation, we can do it, but we have to use integrating factors. And so you can already imagine that this solution is going to get ugly, because the solution for omega is going to have an integral in it, and then the solution for y is going to have an integral in it. So we'll end up with 2 integrals. So this is why I don't like to do the general solution. But to give you an idea of showing you how the general solution would work, you would do this. You would now say omega is going to have the solution something along the lines of like the integral of f of x over a times e to the minus 1x, and then divided by some e to the x term, right? And then you'd say the same thing for y, but it's got an integral in the differential equations. You have to do a double integral, so on and so forth. So you could do the general solution. We are not going to do the general solution.
Would you need like 2 factors of integration?
Yeah, just as before, we're going to have, 2 integrating factors. Yes, you would. Yeah, sorry, I didn't see what you were saying. Yes, you absolutely would need 2 integrating factors. I think I did do the general solution with Zhang and Adrian last year, and they understood it, but it ends up wasting 30 minutes that we don't need to waste, right? So we'll do a specific example from now on. So let's do a particular situation. Let's do the one that we were just doing, but they have the non-homogeneous part thrown in there as well. Okay, so let's solve the differential equation. So we're going to solve. We won't worry about the initial conditions for right now, but let's solve the differential equation. D squared, they use an x. D squared x dt squared plus 5 dx dt plus 6x equals 2e to the minus t. Okay, so this is the differential equation that we're trying to solve. Now, again, there's going to be a hard way, or that's not hard. There's a long way and there's a short way of doing this. Let's do the long way first, and then I'll show you the short way. The short way, again, in this case, is sort of making some assumptions that are kind of tricky to see how you can make them work. So that's why I want to show you the long way first, to show you that these assumptions that we're going to make eventually are not random. It's just like when we solve the second order differential equation the easy way. We start by just assuming we can solve the auxiliary equation, and then just use that the form is of e to the mx, right? And we can add any solutions up together to get the general solution. So our technique eventually is going to be very similar to our homogeneous one, but it sort of seems like you pull some things out of thin air, which we'll eventually see we're not actually pulling out of thin air. No, that's okay. All right. So doing this the hard way, we know that this factorizes, right? We said we could write this as d by dx plus 2 d by dx plus 3 operating on y equals 2e to the minus t. Operating on x, and these are t's. I have a mental problem. These should be different. dt, dt, x minus t. There we go. Okie doke. So we're going to call this thing omega again. This is omega. And so we end up with d omega dt plus 2 omega equals 2e to the minus t. Everybody following me so far?
Uh-huh.
Okie doke. So this is an integrating factor problem. We're going to multiply by mu of t now, which is going to be e to the power of the integral 2 dt, right? Which is, of course, just e to the integral, e to the power of 2t. Okay. Notice how we're using like all of our techniques just to do one of these problems, right? We have to use an integrating factor for first order. Then we've got to use our solutions for second order, right? We're actually going to see that our homogeneous solutions for second order are going to pop out of this as well, right? So I'll show you that in just 1 second. But all of this stuff builds on itself is what I mean, right? So we're doing all of chapter, I can't remember if it's chapter 4 or 5. I think it's chapter 5 for you guys in the new book, and chapter 6 just to solve one problem. All right, so we've got our integrating factor. We multiply through, so we end up with e to the 2t times d omega dt plus e to the 2t, well, I guess there's a 2 here, 2e to the 2t omega equals 2e to the t, right? If we multiply by e to the 2t. Okay, the left-hand side is product rule again. So we have product rule d by dt of e to the 2t omega equals 2e to the t. Alrighty. So, I'm trying to move my keyboard so I have more room to write. All right. So this is what we have so far. Let me plug my iPad in just in case. We integrate both sides. So this, taking the integral of both sides, we end up with e to the 2t omega equals integral of 2e to the t is just 2e to the t, and then we have a plus c. Okay, I'll call this like C1. I'll carry it through. I won't do it seems like you guys don't like it when I say a times 2 is a, so I'll carry them through like this. I'll change them each time. Okay, so then we can find omega pretty easily. Omega is just 2e to the minus t.
Wait, sir.
Yes.
Should I be... Oh, nothing.
Nothing?
I'm kind of confused here. So to get your mu, you multiply everything by e to the power of 2t, right?
Correct. Yeah. And so e to the minus
t.
So
that's okay. Yeah. Yes.
Got it?
Yes.
All right. So then we have plus c1 e to the minus 2t. All right. That's our omega. But remember that omega is actually dx dt plus 3x. Okay. All right, so then we have two versions of omega. Let's set them equal to each other. This is going to give us another integrating factor problem, right? So we have dx dt plus 3x equals 2e to the minus t plus some constant, e to the minus 2t. All right. This is another integrating factor problem, right? So our integrating factor here is a new mu of t. It's e to the power of the integral of 3 dt, okay, which is, of course, just e to the power of 3t. We can ignore the c. So multiplying through, we get e to the t dx dt plus, 3 e to the t. E to the 3t dx dt plus 3 e to the 3t x equals 2 e to the 2t, right? The 3 and minus 1 become just positive 2. And then we get plus c1 e to the just regular t if we multiply by e to the 3t. All right. Left-hand side becomes product rule. So we end up with just d by dt of e to the 3t x. All right, and the right side stays the same. So e to the 2t plus c1 e to the t. And of course, now we can take the integral of both sides. So integrating both sides, you get e to the 3t x equals, I'll write it out, integral 2e to the 2t plus c1 e to the t dt, which, if we can do a relatively quick u sub, this should give us just e to the 2t, sorry, plus c1 e to the t plus c2, right? So another constant of integration. All right. And then dividing through by e to the 3t gives us x of t equals e to the minus t plus c1, right, e to the minus 2t plus c2 e to the minus 3t, which, if you guys are more comfortable seeing a and b, right, that's totally fine. We can write this as e to the minus t plus a e to the minus 2t plus b e to the minus 3t. Okay? That's our solution. So we're done. Here's an interesting thing. This is a really, really interesting thing. This is actually two solutions that have been added together, right? And what do I mean by that? Well, if you look back at the previous version of this problem that we did, which is right here, our solution to this, right? Ignore the particular solution. Our solution, our general solution, was this thing right here, right? It's box. There we go. It was a e to the minus 2t plus b e to the minus 3t. Well, if you look at the solution that we just came up with right now, that's these second two terms right here, right? So somehow the homogeneous solution, if 2e to the minus 2e to the minus t wasn't there, right, part of the solution shows up, okay? So what we typically do is we call the thing that's boxed, we call that the homogeneous solution, and we call the other part, e to the minus t, the non-homogeneous solution, or as your book will call it, the particular integral, right? So we'll...
It is also like divided by 2 the f of x of the answer divided by 2. Does that have anything to do, like the part you add?
Yeah, so the part that you add is not always going to be divided by 2, and it's not always going to be exactly like that. But yeah, there's a very strong relationship here between the form that the f of x is in, or the f of t is in this case, and what you add to your solution at the end. Yeah, it's a good observation. All right, so I'm just letting my Apple Pencil charge for a second. It doesn't usually take that long. It's at 8%. I'll let it charge for 4 or 5 more minutes. But in the meantime, are there any questions about this problem that I've done so far? I'm going to show you an alternate way of doing it, an easier way of doing it. No questions? Okay, good. I'm just going to give it like until 10:07 my time.
So we leave the e to the power minus t just there?
Yep.
Okay.
Yeah, it'll form part of the solution, right?
Mm-hmm.
So it's interesting actually to notice that if you were to just plug in e to the minus t into your differential equation, so if you ignore the thing that's in the box, right? Say that a and b are both 0, right? So if you ignore that part altogether and you just had x is equal to e to the minus t, what happens if you plug it into your differential equation? Well, your second derivative is going to be positive e to the minus t. Your first derivative is going to be minus e to the minus et, or e to the minus t. So you'll end up, when you plug it into your equation, with e to the minus t plus 5 or minus 5 e to the minus t, which is minus 4 e to the minus t, plus 6 e to the minus t. And what do you get when you add those together? You get 6 minus 4 times e to the minus t. That's 2 e to the minus t. So in other words, that actually is satisfying the non-homogeneous part of the differential equation, right? So just the part that's not in the box, so if you ignore the box, if you plug that into your differential equation, you'll get the solution to your differential equation, right? And so why do we even include the part in the box? Well, I'll show you. So say we have, right, a differential equation of the form. Let me just check and see how much battery my Apple Pencil has now. 20%. Perfect. So just say we have a differential equation of the form. Well, I'll label this, right, really quick. So this right here, this is called the homogeneous part. And this is called the non-homogeneous part. Right, so this is called non-homogeneous part. There's a couple different names, right? So non-homogeneous part. right? Sometimes you'll see this called inhomogeneous. Interestingly, this is a time where two prefixes actually work, inhomogeneous, right? But your book will actually call this the particular integral. It's actually not just your book. That's what they call it in the UK, I'm pretty sure. But they still use the terminology homogeneous and non-homogeneous, right? So it is a non-homogeneous part of the differential equation, but it's also called the particular integral, okay? And so oftentimes you'll see me abbreviate this as like y sub h, and this is like y sub nh, right? So the solution for homogeneous and the solution for non-homogeneous, okay? Just so you know it. So I'm going to write down the next page. All right, so let's say, so what are we doing here? So like what's happening? Let's say we have any differential equation in the form, you know, a d squared y dx squared plus b dy dx plus cy equals f of x. And we'll say, suppose that y sub h satisfies, you know, the homogeneous equation. And we'll say, suppose that y sub nh satisfies the non-homogeneous. I said satisfies before. Satisfies. I don't know how I did that. Satisfies. There we go. And satisfies the differential equation. Blah, blah, blah. But with f of x, right? So one of them satisfies it equal to 0. The other one satisfies it equal to f of x. My claim to you is going to be that y, defined as being y sub h plus y sub nh, is a solution. A solution to our original differential equation, which is the same thing as the non-homogeneous. And furthermore, I'm not going to prove this part, but this is actually the general solution.
Sir, I still don't get why the two solutions give another solution, like the sum.
I'm about to show you.
Okay.
Right? So this is what I'm claiming. We have to prove this, right? So what we're going to do is we're going to take this y that I've now defined as being the sum. We're going to take its derivative. We're going to take its second derivative. We're going to plug them into the original differential equation. And I'm going to show you that it gives a new solution. Okay? So to do this, we'll say we have y as yh plus ynh. What about dy dx? Well, this is just dyh dx. And what about dynh? Well, that's just dynh dx. Okay, pretty straightforward. All right, and what about the second derivative? The second derivative is just the same thing, right? Okay, we can take derivatives across sums, so there's no problem there. So let's plug all this stuff into the original differential equation. So if this is equation 1, we'll say plug this stuff into 1. Okay? What's nope, Peter? I can't remember what was happening there at 10:06.
It was like any questions.
Oh, okay. Okay. All right, so if we plug this into our original differential equation, we end up with a, I'll write it out term by term, a d squared y dx squared plus b dy dx plus cy. This is going to equal, right? So let's just plug all these things in. A times brackets d squared y h dx squared plus d squared y nh dx squared, right? Plus b times d, this is really a pain to write, dy dh dx plus dy nh dx, right? Plus c times yh plus y nh. Okay, so if this equals f of x, then it's got to be a solution because we're plugging something into our differential equation and it's giving us what we want. So it's got to be a solution, right? So what we're going to do here is we're going to gather the h terms and the nh terms. So gathering the h terms gives us a times, I don't need brackets anymore. So this is the h term. So a times d squared yh dx squared, and b times dyh dx, and c yh, that's the h terms. And the nh terms are going to be the same thing, but with nh, right? D squared ynh dx squared plus b dy nh dx plus c y nh. Okay. But by definition, right, the way that we've defined YH and YNH, we know that this satisfies the equation equal to 0. So that means that whole thing has to equal 0, right? And also, we know that this whole thing here has to equal f of x, right? So this whole thing equals f of x. And so we end up with, when we plug y into our differential equation, we just get 0 plus f of x, which is, of course, equal to f of x. All right, which this tells us that y, which is equal to yh plus ynh, is a solution, right? Because we plug it in to our differential equation and we get what we want out of it. We get f of x out of it, all right? Does that answer your question, Anastasia, about why a sum is a solution?
Kind of. I just need to assimilate everything real quick.
I get the proof, but just like doing it, I don't know how to say. It doesn't feel natural to sum both solutions, like obvious.
Yeah, it doesn't seem obvious. That's a good point, right? It doesn't seem obvious, but it is true, right? It doesn't seem obvious at first, but it's precisely because of the linearity of the derivative that you can do sums like this, right? Because we've used the linearity in this case, I mean the fact that derivatives can be sort of factored, right? We've used the linearity to plug this in and rearrange the terms. And so we're essentially just saying that the plugging in the homogeneous part is just giving you 0, right? But because there's the potential for the homogeneous part being in there, we've got to include it in our solution. It's sort of like when we gave a motivation for why we add plus c when we do an integral, because when you take an antiderivative, right, the c could be 0, but it could also be anything else. So you have to include it. We're doing the same thing here. The homogeneous part could be 0, but it could also be non-zero, and it would still go away when you take the derivatives, right? So that's why we have to include the non-homogeneous part in our solution. It's like the much more generalized version of plus c, right? That's exactly what it is. Okay, so our question is then, because, repeating the omega stuff every time is a pain, and it's not very efficient. So our question is, well, we now have a robust, quick, concise way of finding h, right? Because yh is the first point there, right? The first arrow that's being pointed to. It's just the homogeneous differential equation. We have a full classification for that solution. We can always find that. So how do we find ynh? And Fernando's observation in our particular problem is actually the answer here. So Fernando noticed that whenever it uploads, or whenever it stops lagging, uploads. Here we go. So Fernando's observation was that the non-homogeneous part of our differential equation solution, our ynh, in this particular example, was of the same form as our f of x, or f of t in this case. So we're always going to make a guess, and this is something that you could prove. Like I said, it might be a good exercise to try and do this exact same problem here with variables, with a, b, and c, and f of x. It's hard, but give yourself a motivation. Tell yourself that there's evidence that whatever your non-homogeneous solution is, it should be of the same form, roughly speaking, as your f of x, right? Or f of t in this case. So let me show you what I mean. Let's do an example. Let's do the same example that we just did a second ago, but now let's do it the easy way, right? Whenever it stops lagging. Okay, so I know we're probably getting tired of the same example. That's fine. We'll do it one more time. Our example is the same one from that past paper question. Now we are actually set up to do the entire question, right? So this is now completed June 2000, what was it, 2009, number 8. Okay. So we have a differential equation, d squared x dt squared plus 5 dx dt plus 6x equals 2e to the minus t. Okay? So this is our differential equation, and we know that there's going to be a homogeneous part to the solution. So we'll say the general solution is going to be x equals x homogeneous plus x non-homogeneous. There's going to be a homogeneous part and a non-homogeneous part. One of them could be 0. They could both be 0 in really weird cases. I don't think that's ever going to happen. Or they could both not be 0, but we have to include the possibility of them both being in there, okay? So there's a homogeneous solution and a non-homogeneous solution. We know that by definition, the homogeneous solution is going to satisfy this differential equation right here. So you don't have to write all this stuff out each time. You just need to have it in the back of your mind, right? So the homogeneous solution is going, oops, not d, I did dx's on both of those. Homogeneous solution is always going to satisfy, well, the homogeneous equation, which is just equal to 0. And the non-homogeneous part is going to satisfy the other one, right? So like the non-homogeneous part is taking care of the f of t, whereas the homogeneous part is taking care of everything else. Okay. Oh, nope, that's not true. Not 0, not 0, not 0. 2e to the minus t. I just realized this should have an h on it. Okay. All right, so this is what we have so far. We know how to find the homogeneous part, no problem, right? We know how to do this. That's immediate. That's from our full classification. We know how to find that. This gives us that x homogeneous is just equal to a e to the minus t, minus 2t, right? Was it e to the minus 2t? And b e to the minus 3t. Okay? We've done that now 3 times. We don't need to do it again, right? Or 2 times. So that's just by using the auxiliary equation, right? Finding our M1 and our M2 and using the fact that our discriminant is going to be greater than 0. So we have 2 distinct real roots. And so our solution is always going to be in this form, right? That's immediate. What about our non-homogeneous part? Well, we don't know. We could do the omega stuff, right? But that's too much work. We could just say, assume that the non-homogeneous part is going to be in the form lambda, right? Some constant times e to the minus t. Okay? So lambda is constant. Now, I haven't proven to you that this is a real way of doing this, but to prove this, you can do the omega proof again. I don't think that there's any point in doing the omega proof. And like I said, you end up with a double integral and it's a pain, right? So we're going to assume that our non-homogeneous part is of the same form. Now, keep in mind, this is not totally unmotivated. There's a reason for doing this. If you look at the left side of our equation, we have some derivatives, but if you forget about the derivatives for a second, we have 6 times x. And so we can't have some other random function be multiplied by 6 that's going to give us something that looks like 2e to the minus t. So it's not unreasonable to think that our solution is something of the form a constant times e to the minus t, right? There's not just a random thing that we're doing here. Although it seems sort of counterintuitive, you can actually fully find these solutions without doing the omega process if you really think very carefully, right? But it doesn't matter. We don't need to think very well or think very hard. We just have to assume that it's in some form, right? And so if it's in that form, what we're going to do is we're going to just plug this into our differential equation. We're just going to plug in to our diff EQ to find lambda. Okay? This is called the method of particular integrals, right? So if we plug this into our diff EQ, that means we need to know the first derivative. So what is the first derivative? This is pretty easy. Our first derivative is just minus lambda e to the minus t. Oops. And then if we plug it into our second derivative, we take our second derivative here, we just get, regular lambda e to the minus t again. Okay, so if we plug that into our differential equation, so plugging in gives us lambda e to the minus t minus 5 lambda e to the minus t plus 6 lambda e to the minus t equals 2 e to the minus t. Okay? So every term has an e to the minus t in it, so we can ignore the e to the minus t's and just see that we have lambda minus 5 lambda plus 6 lambda, right, is equal to 2. Right? Well, no surprise here. We end up with lambda equals, 2 lambda equals 2. So lambda equals 1. And that tells us that if our assumption's correct, which it is, if our assumption's correct, then our non-homogeneous part is just e to the minus t. All right? And so our general solution, for our general solution, all we need is that x of t is equal to our homogeneous part plus our non-homogeneous part, which is just a e to the minus 2t plus b e to the minus 3t plus e to the minus t. Right? Not too bad. So if you notice, that's exactly the same solution that we got the long way, right? That's exactly this solution right here. Exactly the same solution. It's lagging a bit, but exactly the same thing comes out, right? By just assuming that we know the form of the answer, right? We're not assuming that we know the answer, we're assuming that we know the form, okay? How does this feel?
If lambda was equal to 1, oh, nothing.
You sure?
Yes.
Okay. Let's do another. So let's do some examples now. We're prepared to do like more examples. We can now solve.
Sorry, don't we finish at 420?
Oh yes, sorry. I thought we were going to 440. You're right. You're absolutely right.
I can stay longer, but
No. I can't. I have. Oh no, I can. But no. Let's end now. I forgot that we were ending at 10:20 or 4:20, not 4:40. You're absolutely right. So that's perfect. We got exactly through what I wanted to get through. So that's awesome. So tomorrow is Thursday. Tomorrow I'd like to do exercises again, right? So that's what I like to do. I think that's a good plan for Thursdays from now on. Is at least the first hour we'll do exercises before we do anything new, so we can like recap what we've done through the week. All right. So tomorrow we'll do like 4 or 5 problems of this type. I'll try and make it so that I pick some that are going to give us all of our different situations. So things where our roots are real and distinct, things where our roots are complex and distinct, and things where our roots are the same. And I'll try and find some situations where we have 3 or 4 totally different particular integrals, right? So that would mean things like f of x, right? 3 or 4 totally different f of x's. All right.
Yeah, it's cool. I feel like at this time, Mindero más, because tomorrow, like at nighttime, like it's harder for me to understand.
Yeah, I totally understand that. I mean, you guys have already had like a full day of school, and then you're already like despejando when you get home before you have to like start again. I get it, I really do. So that's why I don't want to do any new things on Thursday afternoons. I'd rather just do like a little bit of practice, have it be light-ish, right? So, do you guys not like the Thursday sessions at all?
I don't mind them because like they work for everyone, but I would rather have them early.
Maybe like cut them.
Sir,
them?
I have 5 frees a week, so there's no way I can
Yeah.
put them into school.
I mean, it's fine. It's just when it gets to the end, I'm hungry and tired. But
Yeah, and I mean, believe me, I understand that. Believe me, and I don't want to overdo it. So we'll just make it so that, how about a compromise is that Thursdays will be light. I'll try and save the hard, tedious stuff for this session, for our Wednesday session, and then the light session will be Thursday. Thursday will be more like just practice. I'll probably end up doing a couple of new things, but I'll try and make it so that we do easy new things on Thursday, things that are easy to follow, right?
okay.
And you guys can always tell me, like, I don't want to be teaching, I don't want to be talking if your brain is turned off, right? So please just tell me, like Javier, you just did right now, like just say I can't do anymore, because if you can't do anymore, there's no point in doing anymore. And I don't mean that in like an angry way. I mean in like it's just not efficient to do it that way. we have plenty of time, right? We're more than halfway done with FP2, so we're in really good shape. We're fine, so don't stress. If you can't do any more, you can't do any more. There's no shame in that, all right? So just if you get to like halfway of the Thursday session tomorrow and you just say, I just can't go on, send a message and we'll just stop, all right? I promise. I'm not going to be crazy about it, I promise, all right? Okay, guys. So sorry for going a little bit over. Javier has asked me to recap some of this stuff tomorrow, so I absolutely will, right? I'll recap it, and then we'll just do like 3 or 4 problems of it, and we'll see how we feel after that, all right? All right. Bye, guys.
Bye, sir.
Bye.
Yes, sir.
Have a good day. Bye-bye.